Hello, and welcome to the Freemelt podcast, Powder to Product, where we dive deep into the world of metal additive manufacturing with a focus on electron beam powder bed fusion. From academic research to industrial applications, we take you layer by layer through the AM journey. My name is Arun, and I'm your host for the day. I work as a senior material scientist at Freemelt, the manufacturer of open source and open architecture electron beam powder bed fusion systems. Our guests today are from reputed organizations in the world of metal AM, and together with them, we are going to learn about processing tungsten, a challenging material for AM. Welcome, William and Michael.
Thank you, Aaron, for the invitation. So my name is William. I'm a PhD student based in Östersund, so working at Mid-Sweden University. And my project is about working with material development for electron beam powder bed fusion. So since we got the Freemelt last year, I've been working a lot with process development on this system. And I've also got previous knowledge in the Arkham systems. So I really like pushing the limits and trying stuff that people have said is impossible. So that has led to a lot of modifications and stuff to our system. So we've done some water cooling in the chamber and separate heaters and other tweaks to get the most out of the system. And outside of the research, I also run a printing bureau where I help industry to design for additive manufacturing and also produce some parts for them. And we also develop our own products. So I do a lot around additive manufacturing, basically.
Yeah, thanks, William, and thanks, Arun, for the invitation to be part of this podcast. So my name is Mikael Schuiski. I work today as a business development manager for our powders for additive manufacturing. I have more than 10 years experience within the field of AM. I've been operating our AM service center that we had in Sandviken. I've been with Sandvik for more than 20 years. I hold a PhD in inorganic chemistry from Uppsala University. I think it's super interesting, this topic, and it's an interesting material to work with. So I'm really looking forward to sharing our experience in this collaborative project that we have.
Yeah, welcome once again. You both have long experience in AM, which is also exciting to be part of this cooperation project and contributing from Freemelt's side as well. So William, we are going to talk about your recently published article on processing of chemically reduced tungsten powder. But starting with the big picture, what is it that you're to solve for tungsten additive manufacturing?
Yeah, so the article contains the different parts. So one thing is that we want to produce, of course, chemically reduced tungsten, which we'll come into later, I think, but it's a much cheaper powder, which adds some difficulties to the process, but we managed to make 100% dense material, or close to 100% dense. And the other part is that we want to increase the efficiency of developing material parameters. So if you look at our previous publications, you can see that we produce many hundreds of blocks with one setting in each block, and we have to analyze each block. So here we wanted to do all the settings within one block instead. But since we also did spot melting, it turned out that we made kind of two blocks, and then we also wanted to investigate changes if we go from high current to low current or from low current to high current. So we also flip the blocks upside down. So we have 4 individual blocks, which we vary the settings within to find optimal parameters in the most efficient way. And we went one step further. So we, in this case, we analyzed the samples, but we want to avoid that in the future, or at least minimize it to increase the speed. So we also used the backscatter signal and analyzed this signal to see where we have good material and bad material to demonstrate how we can use this in the future to develop process parameters more efficient.
There's quite a lot to unpack. Let's start with the interesting strategy for minimizing the number of trials with as fewer experiments as possible. You call this dual gradient approach for process parameter development, and you mentioned that you have 2 blocks and you're changing parameters. Is this something that you're doing on the fly, or is it pre-planned? And what's been the motivation for this, or where have you inspired
Yeah, so our goal is to make it fully automatic, but in this case we're trying to demonstrate. We've been thinking about this for several years, but it's been very difficult to do. We tried it in an old system, but there we could not make this, or we didn't have this open source beam path, so we had to section the files into many thousand STL files, and then manually put the setting on each part of the build block. And it turned out that it's not so easy to make that work. But now when we have the open beam path, we can make the files as we want them with some limitations, but pretty much as we want them. And then the idea is that, for example, in the spot melting, we can vary the dwell time. So even though we have random spots, we can in one side of the block have a very long dwell time, and in the other side a very short dwell time. And then we can also vary the current throughout the layers. And of course, there's many hundred settings, but in this case, we went for the dwell time in the spot melting and the beam speed in the line melting, and then the current as the layer increases or layer height increases.
So sort of not only within the layer, but also there's a gradient in the Z direction. So if I understood the paper correctly, then you're looking for a diagonal across each block.
Yeah, exactly. So when we cut the blocks, we can actually see the optimal material within the diagonal, somewhere within the diagonal. So since we are doing the manual cutting and analyzing here, we need to keep the settings somewhat, we have to have an area to analyze. But if we in the future manage to use the backscatter even more, then maybe we can vary even more settings throughout the build. But here we have to keep a few of them locked, so we have something to look at in the microscope.
Open source, but still you have to plan and limit the number of things that you want to try within each build. So interesting approach. Really enjoyed reading that part. So now going back one step, starting with the precursor. It's a really interesting powder, chemically reduced tungsten powder. All of world's tungsten starts as chemically reduced powder. What does this mean, or how do you see this, Michael? Starting with this powder and having seen what you have seen in the progress.
I think it's we talk chemical reduced powders. I mean, there's been work done with spheroidized tungsten powders for some time, but we really need to find a cost-effective solution for using these quite expensive powders then to make sure that we get, open up the possibilities for business cases for certain parts. And I think, we produce a lot of tungsten within Sandvik. This is an important element for us, maybe the most important element. And I think what William has proven here is really interesting to see that you can take it more out from the chemical plant where we do this and put them directly into a printer, even though having not as good flowability as a spherical powders, but still with the right technical solution, it's possible to get really high dense parts, which opens up doors for new application, which is, I think, the whole purpose for this project.
Certainly. What I've enjoyed, or my interpretation is from this work, a flowing powder doesn't necessarily mean that it is spreading well. And even though the powder is spherical and so on, spreadability is not anyway measured in any tests, any of the standard tests. And here what he has shown is, the powder doesn't flow according to the standards, but it's still spreadable and it's still printable, and not just printable, but printable to achieve excellent density. So that's really interesting.
Absolutely. Sorry there, but you can also see from other types of AM technologies, such as binder jetting, which we have worked with. You work with really fine powders that are not flowing as well as the normal E-beam powders do. And then with the right type of spreading technology, you can get the powder bed of that. It's an engineering question.
Very true. Very true. You also mentioned that you have tungsten is one of the, or if not the most important element for you, and you have worked with it quite a bit. But you also have the possibility of securing supply in Europe and also in the North America.
Yes,
Can you tell us a little bit more?
Absolutely, Arun. Sandvik invested in Wolfram Bergbauenhytten some years ago. This is our tungsten production unit, but it also includes a tungsten mine in Austria. So we have a local internal supply of tungsten ore. However, we also source from other parts, and we do a lot of recycling. We have had for a long time a big target project investments and everything to set up the structure to recycle used insert from our customer back to the plant in Austria. We have a recycling plant in India also, should be said. But this really saves a lot of energy in our production, so we can significantly reduce the energy consumption in the production of the pure reduced tungsten. So this also makes it for us then keeping a control of what I've said before, one of the most important element for Sandvik. We have also invested in Buffalo Tungsten over in the US to set up more production lines in North America as well for our powders.
Excellent. It's the recycling part where we, okay, on one side there's quite a lot of builds that we do for experiments and so on. Crashed builds, start plates are in tungsten and so on. So it's good to know that there is a possibility to have them recycled and sort of have this closed loop, addressing some sustainability issues of powder usage and scrap material handling and so on.
Absolutely, I think this is a way of thinking for production in the future. We should not look at scrap. We should look at it as a secondary raw material that we can, if sorted well, this is a high value material that can go back into production. And this goes especially for, if you look at Europe, we have identified critical raw materials that we need to keep an eye on, and tungsten is one of them. So I think this is definitely in line with what is needed to do in Europe.
Yeah. So we've now so far discussed the process development strategies and this raw material that goes into process development here. Now, looking at the other part of the work that William has been doing, using backscattered images. It's very good with tungsten, isn't it? It has quite a high backscatter coefficient, so the images are crisp, meaning the actual signal itself is of high quality, and you can use it. And tungsten is a good radiation blocker. It's used in radiation shielding in medical imaging and other fields. Therefore, it's a bit challenging to do non-destructive evaluation of printed parts. Yes. And can you tell a little bit more? Because you say I can give a report that says per layer this material is good. So how does this play into an industry setup, say more complex parts and so on? Can you elaborate a little bit?
Yeah, if we save, we can have an image, so we can have like a 3D view of the component in case we have a defect or we have maybe a probability that we have a defect in some layers. We can have that marked out. And then maybe we need to define if it's a critical area of some component, then we need to scrap it, or maybe it can be used anyways, but we know that if it fails, we can look back at the build file and see what might have happened and how we can improve future components, for example.
This is very, very useful. Towards qualification and industrialization of this process, we are working with a completely new material, completely new way of process development. So I'm just trying to tie this all together. Michael, how do you see these two things? For some new powder using an open architecture system and possibilities.
No, I think it's really nice to hear that we are starting to think of really smart ways to doing machine learning here to work with this. And then, of course, as I kind of mentioned before as well, using this low cost or this cheapest possible powder coming directly from the chemical plant compared to something that has been more added value in plasmodized or going through a bar or a wire, wherever to make the powder. I think it is this will be when we're starting to look at application for imaging or for shielding. Cost will become a factor that we need to take into account. So how we can speed up and quality assure inside the process is super important. And then, yes, a heavy element like tungsten is not that easy to do to look at after it's been printed. And it's also brittle sometimes. So it is a tricky material. So I think we're on the track, and whatever we can do in situ is super good.
Yeah, it's because the benefit with additive for a difficult material like tungsten is that you can actually make complex parts that you wouldn't otherwise be able to do via machining. And, having it in situ monitored and, proving that this is a good part is of absolute importance to, take this or make this process industrialized and realize even more applications. William, talking about industrialization, you mentioned in this paper one of the melting strategies is better for scaling to be able to produce bulkier parts.
Yep.
Why is it, and what is it that you found to be the underpinning factor that helps the scaling?
Yeah, so we tried line melting and spot melting in this case, and we found that line melting is very difficult to scale. And if we look back at welding, it's maybe easy to understand because you never weld like a very long line. You do like segmented welding to avoid the part to warp. And it's similar here, that if we melt a very long line, then the thermal contraction will be over the whole line, so the whole block in this case. But by doing like local melting and solidification, we can reduce the strain on the part a bit. And I also think that the line melting and spot melting in terms of like scaling for different geometries is a bit different, because in the line melting you have to take care of the line length, because you have to reopen the melt pool for each line, so you have to compensate how fast you're going or how much energy you're putting in if you're changing this line. But for spot melting, you also have to change, of course, but more depending on the area, if you're doing randomized spots at least. So I think it's much easier to adjust the parameters to use it if you have a complex geometry and use spot melting. So it will be very interesting, I think, to see how people use spot melting in the future. But I see large potential in using this.
Yeah. That's very good to hear, because we ourselves believe spot melting is the way forward, but also someone else having a similar opinion is really encouraging to hear.
Yeah, I mean,
I'm a spot. Oh, sorry, go on.
No, I mean, it depends a bit on what you want to do, but for sure, at least in many cases, such as these crack-sensitive materials, I think spot melting is a great way to go forward.
Yeah, I totally agree. And Michael, here's something that we think. I mean, firstly, we say our systems are open source and open architecture. So William has been able to use, imaging and other aspects, and also really process develop, using the open beam path to, show a very interesting way for process development. But what we have also done is to use a powder that has not been used, and we are opening a new area for, cost-efficient powders. That's something that we touched upon earlier. I mean, this is something that we have done and proved for tungsten now. But how do you see this sort of affecting the AM world? I mean, does one require spherical powders still, or could, water atomized powders or other powders actually take a larger share of the metal AM?
I still think we will need gas atomized powder for quite a lot of the technologies. I can see water atomized coming in, but we will have other issues there with purity of the powder as well. So I think it's just showing that we should not be focusing on a single atomizing process or powder production process. The more we can open up the doors to show that, yes, you can work with this semi-spherical or kind of irregular shaped powders in an advanced process, yes, that would be good. But I don't think it will be applicable for all types of materials. It also, it's the requirement of the parts that should be done. If you need high purity, then you will stick to the vacuum melted or argon atomized powders available. So I think it's all depend on.
Yeah, very good point. And I want to, expand a little bit on something that you mentioned here. It's going to be application specific, and purity is something that you touched upon, chemical purity. So what do you see? I mean, having looked at these promising results, what do you see are the future problems to solve to make this process more industrialized?
I think the first thing, from this first study done by William and the team up in Östersund, I think the next step is to start looking at features that can be implemented by industrial use for this, if it's for X-rays imaging, for collimators, or if it's for shielding. These are the next things to get the feedback from somebody who will put this into an industrial use. I think that will be very important for us to get into the project and for general using these type of powders for E-beam.
Yeah, and William, what do you think are the next research problems that you would be focusing on?
We're continuing to work on a similar thing to develop it to be more automatic, but on other alloys currently. So I hope that it will be kind of a machine learned system, as Mikael said, that you can just, it will still need a lot of thinking before you do it, but you can put the material in and run a build, and hopefully you can get something out which represent the process window, and then in a more efficient way work towards optimizing this. Yeah.
Yeah, where do you see the first commercial impact of this happening? Any specific fields? We've talked about imaging and medtech and radiation shielding and so on, but do you foresee something where this will be adopted first?
First I would assume it's probably like X-ray and military applications because of funding reasons, but I see huge potential in the energy sector as well, and I know you have some projects on that, so maybe you have something to say about how it can be used in energy, but shielding, I guess, is one big opportunity for tungsten.
Absolutely. For energy side of things, we have been working actively with the United Kingdom Atomic Energy Authority, Fusion for Energy, where we have active projects, and implementing what you have shown possible, and taking it forward within the energy sector and the fusion energy sector will be very interesting. So I look forward to continuing this journey with this partnership. And on that note, let's wrap it up here. It's been a pleasure talking to both of you, and thank you both for your time, sharing your insights from your vast experience. So thank you once again.
Thank
you, Arun. Thanks a lot for having us on board.
Next time, we'll dive into another research topic, and make sure to follow Freemelt on social media for the next episode. Thank you.